Let us now consider the news vendor model. This model is a single period model with stochastic demands. And the name comes from a news vendor who has to determine at the start of the day how many newspapers to put on stock. And then during the day he will observe demands, but then the amount of newspapers cannot be changed anymore. The model is also useful in other areas. So for instance, if you talk about perishable goods, so meals and cafeteria and dairy foods, but also for products that have a short selling season. So for instance, Christmas trees. Already long before the Christmas season, we need to determine how many Christmas trees to plant. And then if the demand turns out to be higher than expected, then we cannot plant additional Christmas trees anymore. The notation that we are going to use is capital D for the demands. That's a random variable. The cost per unit that we pay will be denoted by C, and then we are selling the units for a selling price P that is larger than C, and then the difference between the two is relevant because that's kind of the profit that we make. If we have products left at the end of the period, they will have a salvage value, and that will be denoted by small s. The salvage value can be 0 if there is no remaining value, or can also be negative if there are costs involved when throwing things away. And then we have the decision variable, that will be the order quantity, and that is denoted by y. So it's a single decision variable for this model. And then the number of units that we sell is the minimum of y and d. So if we've ordered less than the demand, then we will just sell everything that we have ordered. So then it's y. And if the demand is less than what we have ordered, then we have some products left. And then we will only sell capital D products. This minimum is random because the capital D is random. And the more products we buy, the more we can of course sell. But then there's also a higher risk that we have products left at the end of the day. Then the analysis. So we would like to minimize the total cost. And there are two cost components in this model. We have a cost C minus S, so the difference between the price that we pay and the salvage value. That is a cost that we basically have to pay if we have units left at the end of the period. We will give that a symbol, the H, and this is called the overage cost. So it's C minus S. And there's also a cost for lost profit basically, so P minus Z. This is our profit per product. If we don't have enough products to meet demand, then we have kind of a missed profit. So this is then the cost, P minus C. That's the that's the underage cost, and that's denoted by B. So B is P minus C. And now we would like to minimize the total expected cost. So then we need an expression for the total expected cost. So we are going to multiply H by the expected number of items left. And we are going to multiply our underage cost by the expected shortage. Mathematically, we can state it like this. So we see expectation. What we also see is the plus operator. And the plus operator gives us a positive part of something. So the positive part of x is x itself if x is positive, and it's 0 otherwise. So what you could do is you could write 3, and then the positive part of 3, that's just 3. If you have minus 3 and you take the positive part of minus 3, then it's 0. So that's basically what this plus operator does. And we need that here because then we get that this is the expected amount of items left. And then this is the expected amount of shortage. We have items left if y is greater than d. And then y minus d is the amount of items left. But y minus d is only the amount of items left if that's positive. So if y is greater than d. So if it's the other way around, then it's negative and then we don't have anything left. So then we should not incur that overage cost. And also the other way around for the underage cost, that should not be incurred if d minus y is negative. Because the underage cost is for shortage. If the d is smaller than y, or you can also say if y is larger than d, then we don't have a shortage. So this is exactly what we would like to have. And then it's also possible to show that the function capital G is convex, and that means that the minimum is attained at the point where the function goes from decreasing to increasing.